Okay, this time around we're going to take a look at finding the zeros of a polynomial function. Last time we talked about polynomials, we just went through all the vocab associated with them, what their degree was, how to figure out some important features of their graph when we go to plot, all the solutions to a polynomial function on the coordinate plane. So this time around we're going to take a closer look at how to find the zeros of a polynomial function, specifically the real zeros. So we want all the x values for which the polynomial's y value will be 0. You guys have done this with first degree and second degree polynomials, so linear and quadratic polynomials. So for a linear polynomial, it's pretty straightforward. You just plug in 0 for y and quickly solve for x. And for quadratics, you can use the quadratic formula. That would always work and always give you the two zeros of the quadratic polynomial. So, but what if the degree is 3 or the degree is 4 or 5 or something larger than degree 2? Well, it gets a little bit more complicated. So we're going to start to walk down that path in this video. So let's quickly review how this would work for polynomials that we are already kind of comfortable with. So for this first example, we're going to remind us that factoring is a very useful tool when looking for the zeros of a polynomial. So for this first one, we've got a second degree polynomial. And since it's second degree, it might factor quickly over the integers. So let's see if we can't make that happen. So let's do our two linear factors here. And let's see, factors of 6. What if we try 3 and 2? And then factors of 4. If we do 4 and 1. So that'd be 8 and 3. That could potentially give me a -5. So what if that was minus, and what if that was plus? So that'd be 6x squared, and then -8 plus 3 is -5, so that should work. So then if I plug in 0 for y, I can use the zero product property, which says that each of those factors could be 0, and then the product would be 0. So then x is 4/3 or -1/2. So my zeros, both multiplicity 1, are 4/3 and -1/2. Now those are both real numbers. So if I were to graph that quadratic, I would already know where it intersects the x-axis at. Let's look at b. B is a cubic or degree 3 polynomial. However, we don't have to do anything particularly fancy to factor it. So these first two terms both have an x squared. So the greatest common factor of the first two terms is x squared. And the greatest common factor of the last two terms is 1. And then now we see the greatest common factor of the entire polynomial is x minus 5. Then we want the zeros, so we'll plug 0 in for y. We can use the zero product property once more to see that one of the zeros is 5, and then the other zeros are I and -I. But those are non-real, and we are interested in just the real zeros. So I only have 1. It's +5, multiplicity 1. And that should not be a surprise because it's a degree 3 polynomial. So we know that with a positive leading coefficient, so that we know that the far left of the graph points downward and the far right of the graph points upward towards the headed towards positive infinity on the y-axis. So the graph has to cross the x-axis. It would be, you can't draw that without it crossing the x-axis. So the fact that we actually got a real 0 should not be a surprise. Whereas for a quadratic, lots of times those don't cross the x-axis, so we don't always end up with real zeros. Our example we did, but sometimes we get two non-real zeros for that. But for B, where we had this odd degree polynomial, the fact that we got a real zero out of it, not a huge surprise. Well, those two weren't bad because we could actually factor them. So they factored nice and neat over the integers, so it wasn't too difficult to find those zeros. But what if you can't quickly factor it? So if we peek ahead a little bit, this next example, 6x cubed minus 19x squared plus 16x minus 4, that one's not going to factor quickly. So what can we do instead to try to help factor it? So what we're going to do is we're going to steal something we did back in elementary school. I'm going to borrow it. So let's say you were trying to factor 657 into its prime factors. Well, 11 plus 7 is, what's that, 18? And 3 goes into 18, so we know that 3 is going to be a factor. So that means that 657 is equal to 3 times some other number, because we know 3 goes into it. Well, what if I want to find that missing number? Well, I can just divide both sides by 3. I could just divide 657 by 3 and get 219. So that tells me that once I figure out that 3 is a factor of 657, I can use division to see that 219 is yet another factor of 657. So this is kind of a hint as to how we can factor complicated or high degree polynomials. So let's see that in action. So let's say I've got this cubic, 6x cubed minus 19x squared plus 16x minus 4. And what if I divide that by x minus 2? Now, why did I pick x minus 2? Because I know it's a factor, and I know you guys don't necessarily know that, but that's fine. We'll talk about how to come up with that factor a little later. But for now, let's just see that division is going to help me factor that cubic. So let's go ahead and divide those two. So I'm going to do 6x cubed minus 19x squared. So here's my cubic polynomial. Then we're going to divide that by x minus 2. Recall that when you do your division, the highest degree term has to go first, then the next highest, then the next highest, then the constant, and don't skip any degrees. So if you're missing a term with a certain degree, just go ahead and put a 0 in its place. So like if we were missing this linear term, we could put 0x. So we need all the degrees there for this to all line up. All right, so now we're going to do our long division. So x times 6x squared. So x times 6x squared is 6x cubed. So you're looking for a term such that when you take that term times this leading term of the divisor, you get this leading term of the dividend. So 6x squared times x is 6x cubed. Then we go ahead and multiply this whole thing times the entire divisor. So 6x squared times negative 2 is negative 12x squared. And then we subtract, just like in elementary school, and get negative 7x squared. And then, just like in elementary school, we drop down the next number, and we repeat. So then we say x times negative 7x would be negative 7x squared. And then we got to take negative 7x times everything out here. So then we're also going to get a 14. Yep, that's right. 14x. And then we're going to subtract. And then let's see, we're going to get 2x. And then we drop down the next number. And then x times positive 2 gives me 2x. That times that's my negative 4. And then we subtract. And we get 0. There's nothing else to drop down. The way you know that you're done with your division is when the subtraction produces a polynomial whose degree is smaller than the divisor. So since this is degree 1 and this is a constant, which is degree 0, I know that I'm done. That's my remainder. So my remainder is 0. My remainder is 0. So let's go back and look at our example from arithmetic. So if I take 657 and I divide by 3, it goes in evenly, meaning it goes in without a remainder. That's how we knew that 3 was a factor, and that's how we know that the quotient, 219, is also a factor. So I just did some division and got a remainder of 0. That's important. So since the remainder is 0, we know that the divisor, which was x minus 2, and the quotient, which was 6x squared minus 7x plus 2, are factors of the dividend, which was that cubic. In other words, I now know that this cubic can be factored into x minus 2 times 6x squared minus 7x plus 2. Now that's a quadratic, and we know that sometimes quadratics can be factored using integers, and it turns out that this one can. And lo and behold, we just showed that this cubic polynomial in standard form can be written this way in factored form. So this is standard form, and this is factored form. So we consider this completely factored over the integers. I cannot write that in any factors that are a lower degree than what I've already got, and I'm using all integers. And I was able to do that using division. Now, that said, not all division produces a remainder of 0. So the same is true for polynomials. So if I divide x squared plus 3x plus 5, if I divide that by x plus 1, well, x times x is x squared, 1 times x is x, and then when I subtract, that's 0, that is 2x, and then I drop down my next number. X times 2 is 2x, and then 2 times 1 is 2, and then I subtract, I get a remainder of 3. Now I know that's the remainder because that's a degree 0 polynomial and the divisor is a degree 1. But I get a remainder of 3. So just as in arithmetic, I now know something about the factors. So, back when you did arithmetic, if you had 7 divided by 3, 3 goes into 7 twice with a remainder of 1. So that tells you that 7 does not factor into 3 times 2 because there was a remainder. So 3 and 2 were not factors. Well, now we know that x plus 1 and x plus 2 are not factors of that quadratic. So since the remainder is not 0, x plus 1 and x plus 2 are not factors of that quadratic, which was x squared plus 3x plus 5. Now, keep in mind, all that mattered is that the remainder wasn't 0. I don't care that the remainder is 3. It just mattered that the remainder wasn't 0. Okay, so again, taking our cues from arithmetic, if you divide two numbers and you get a remainder, so like, here's an example from arithmetic, 15 divided by 7. Well, 7 goes in twice with a remainder of 1. So after you do your subtraction, you get a remainder of 1. What that actually tells me is that this improper fraction, 15/7, can be written as 2 plus a little bit more, because 7 goes in 2 times, but there's some left over. So it goes in 2 times plus 1/7 more. You guys might have called those mixed numbers in elementary school. I don't know what they call them anymore. But all that really matters is that we can take this improper fraction and show that it goes in 2 whole times with a little bit left over. So it's 2 plus 1/7. So if I was to add those together with a common denominator, I would get 15/7. Well, the same is true for polynomials. I can do that exact same thing. So here's the one we just did in the previous example. So I'm not going to do that division again. But what that's telling me is that this improper rational function, because look, it's top heavy. We got degree 2 over degree 1. So it's improper. What it tells me is when I divide that, I get x plus 2. That's kind of like my whole number. But I have a little bit left over. I had, so just like up here, I had 1 as my remainder, and then 7 as my divisor. Down here, I have 3 as my remainder, and then I've got x plus 1 as my divisor. So again, we're just stealing from arithmetic, because again, algebra is just generalized arithmetic. That's all it actually is. So I get, again, if you want to call it mixed number form, go for it. I don't really care what you call it. But I can take this improper rational function and write it as x plus 2, which was the quotient, plus the remainder over the divisor. So this is the quotient. This is the remainder. And this is the divisor. And that's why when you get a remainder of 0, you actually find factors. Because if the remainder is 0, then this whole fraction just equals 0. So there isn't any left over. There's no little bit extra. It just cleanly factors into the divisor times the quotient. So in general, again, this is the same thing as back in elementary school. In general, the dividend, so the dividend is what's under the division sign. So for my arithmetic example, that'd be 15. We know that 15 equals 2, the quotient, times the divisor plus the remainder. So I would take the quotient, which is 2, times the divisor, which is 7, plus the remainder to get 15. So in general, the dividend is simply the quotient times the divisor plus the remainder. And if the remainder is 0, then the quotient and divisor are factors of the dividend. You can actually see it right here. That's why I have it written out this way. If the remainder is 0, then you just have the dividend equals these two things times each other. Well, that's what factors are. Factors are the things that when multiplied produce a product. So the remainder is key. That's what we're looking for. So this is called the division algorithm, is the fancy name for it. Not that we need to know the fancy name, but for those that are curious. Okay, so now we can write some of this down formally. So again, names aren't super important, but there is a name for this. So we'll go ahead and give it. So the remainder theorem says that if a polynomial f is divided by a linear factor, x minus c, then the remainder will simply be the y value for that x value. So if you take any polynomial and divide by a linear factor, then you can actually see what the remainder will be ahead of time. So if you didn't want to actually sit and do all the division, you could just simply say, okay, look at this factor. The 0 from it is x equals c. And if I just take that x value and plug it into the polynomial to see its associated y value, that will be the remainder I would get if I actually sat and did the division. So it's essentially a way to kind of get a peek at what the remainder will be without having to do all the division. So for example, let's say I have this cubic and I were to divide it by x minus 3. Well, I could sit and do all that division, but if I just simply want to know what the remainder would be, then I just need the 0 from this. So the 0 from this would be x equals 3. And then I could just plug that into this cubic. So if I were to plug 3 in to this cubic, I believe, if I do my arithmetic correct, that comes out to be negative 14. So that would be the remainder when I divide those two. So if f is divided by x minus 3, then negative 14 is the remainder. Now, why would I care? Because since the remainder is not 0, I know that x minus 3 is not a factor of f. That's the important part here. Well, what if I divided it by x plus 2? So then the 0 would be x equals negative 2. Well, what would happen if I plug that in? So if I plug negative 2 in, again, assuming I do my arithmetic correct here, square that, I believe that comes out to be negative 29, which is not 0. So once again, I know that x plus 2 is not a factor of that cubic. So I would be looking for the remainder to be 0. That's what I want. So this tells me that x plus 2 is not a factor of f because the remainder isn't 0. Well, that leads us to our next theorem, which says that the linear polynomial x minus c is a factor of polynomial f if you plug the 0 in associated with that factor and you get y equals 0 for the whole polynomial. In other words, it's just what we said up here. If I was to take the 0 from this linear polynomial, plug it in, what I get back out, that y value, is going to be the remainder when I divide. Well, if that remainder is 0, I just found a factor. So let's try it. So for this one, determine if x minus 1 is a factor of that cubic. So this has a 0 of x equals 1. So let's plug that in. So 2 times 1 cubed, 1 squared, 2 times 1 minus 3. And that works out to be 0. So by plugging a 1 in, and its associated y value is 0, I just found a 0. So this all just, it's one big, we're kind of wound our way back to what we started with in the last section. When you plug in an x, if y is 0, you just found a 0. That's the whole idea. So I plugged in 1, got y equals 0, so I just found a 0 of this whole big cubic polynomial, which means x minus 1 must have been a factor, which is something we talked about in the last section, where if you know a 0, you can work backwards to its factor by doing x minus that number. So x minus 1 is a factor of this cubic. Well, what about x plus 2? All right, so it's 0, it'd be negative 2. So let's plug negative 2 in. Again, this all hinges on me not screwing up the arithmetic. I believe that works out to be negative 27. So x plus 2 is not a factor of our cubic polynomial. It's a factor of something else, but it's not a factor of that particular cubic. Okay. Well, it turns out you can actually predict about how many real zeros a polynomial will have. So it'd be better to say you can kind of put a restriction on the number of real zeros a polynomial function can have. So a polynomial with real coefficients, which are the only kind of polynomials you've ever worked with. So a polynomial with real coefficients of degree n, so its degree is n, has at most n real zeros. So if you have a degree 3 polynomial, it has no more than 3 real zeros. If you have a degree 27 polynomial, it has no more than 27 real zeros. Now it could have less than that, so let's not gloss right over those two words. At most n real zeros. So that's handy because when you start to go look for the zeros, you at least have some idea of about how many you're looking for. You at least have an upper bound on it. Well, how do you go find zeros when you've got a high degree polynomial that you don't know how to factor? So if you've got some degree 5 polynomial that you're looking at, you're like, I don't know how to factor that, so I don't know how to go find the zeros. Well, we got some things that'll help. The main tool we have is called the rational zeros theorem. So this is going to be our main tool to factor high degree polynomials, and so we'll just write it out first. It's going to be a lot, but we'll make sense of it. So if a polynomial with integer coefficients so it is kind of specific. You have to have integer coefficients. So again, don't read right over that. That's important. Has any rational zeros they will be of the form p divided by q, where p is a factor of the constant term of the polynomial, and q is a factor of the leading coefficient, which apparently I can't spell. So there's some key verbiage in here that we got to pay attention to. First off, your polynomial has to have integer coefficients. So the coefficients of the polynomial can only be the counting numbers, 0, and their opposites. The other verbiage that we don't want to just read right over is if a polynomial has any rational zeros. If it does, because there's no guarantee. Some polynomials have all zeros that are not even real numbers. Some polynomials have zeros that are all irrational. Some polynomials have zeros that are all rational. So there's a hodgepodge of what's possible. So this particular theorem is only for polynomials with integer coefficients, and then it's only helpful if the polynomial has some rational zeros. It turns out quite a few polynomials meet these conditions, so it's still fertile ground in which to play here. So let's give this a whirl. You'll notice you've got quite a bit of room to work, and that's on purpose. So don't write largely. Keep your font small. So let's look at this cubic here. 2x cubed plus 11x squared minus 7x minus 6. So it's definitely a polynomial. Those are definitely integer coefficients. So if you look at that and you think, I don't have any idea how to factor that, so how am I supposed to go find the zeros? That's okay. That's what the rational zeros theorem is going to help us do. So my constant term is 6, negative 6 technically, and my leading coefficient is 2. So my factors of p, so remember it said p has to be a factor of the constant term. Well, the constant is negative 6, and then q is a factor of the leading coefficient. So my factors of p are 1, 2, 3, and 6. The only numbers that go into 6 evenly are 1, 2, 3, and 6. But we're working with integers. So the positive or negative version of 1, 2, 3, and 6, those are all fair game. So positive 1 would go into 6, negative 1 would go into 6. That we don't really care about whether 6 is positive or negative itself. We just care about all the integers that would go into that evenly. So positive and negatives both are fair game. Well, the leading coefficient is 2, so the factors of q, well, the only integers that go into 2 evenly are 1 and 2. So here's where the rational zeros theorem comes in. It says if this cubic has any rational zeros at all, they will be of the form p divided by q. So if I take all these p values, 2, 4, 6, 8 of them, and divide by these 4 q values, I'll create rational numbers, because integers divided by integers are rational numbers. That's what a rational number is. So if this cubic polynomial has any rational zeros, I know exactly which rational numbers they could be. So we're going to call these possible rational zeros. And they are formed by doing p divided by q. So don't overcomplicate this. I'm simply taking these p values and dividing by these q values. So this list I'm about to create should not cause your eyes to cross here. So if I take 1 and divide by those, if I take 2 and divide by those, 3 and divide by those, and then 6 and divide by those. Now you don't have to put repeats. So like 6 divided by 2 is 3, but I already got 3 in there, so there's no need to put it twice. So this list, 2, 4, 6, 8, 10, 12, there are 12 rational numbers that if this cubic has any rational zeros, it has to be one of these 12. Has to be. So that's kind of the big takeaway here is if f has any rational zeros, they are in this list. Now, it may not have any rational zeros. I mean, that'd be kind of mean of me to do that with the first example, but it might not. We don't know. So we're going to have to go check. And by the way, if we check them all and none of them work, we either made a mistake or this cubic polynomial has all irrational. Maybe not all, but it has no rational, which means it's going to have at least one irrational because it has to cross the x-axis. It's an odd degree polynomial. The other two could be non-real, or the other two could be irrational. So we're just checking to see if it has any rational zeros. Well, how do we know? Well, to check if these are zeros, you simply plug them in and see if y equals 0. I mean, that's That's the definition of a zero, is it's an x value for which y is 0. So we got 12 to try. We have calculators. That makes the arithmetic go quickly. You'll notice, though, that the book tends to pick ones. So as we kind of get the hang of this, the book tends to pick ones where if you kind of start with the smaller numbers and work your way up, you're probably going to find them quicker than if you start with the bigger numbers and work your way down. So like I would recommend starting with 1 and 2 and 3 before you bother with 6. But it just kind of depends. You'll see what I mean as you practice these. So for this particular one, let's just try 1. Let's just try our luck and see if positive 1 works. So if I plug in 1, I'm going to get 2 plus 11 is 13, minus 13 is 0. Look at that. So if I plug 1 in, I get 0. So the very first one we try. Look at that. It's almost like I planned it. So that tells me that x equals 1 is a 0, and x minus 1 is a factor. Well, now we're back to that very first example that we did, which I know was way back here, but we're going to go look at it anyway. Once you know a factor, division can tell you other factors. So the very first example, I said, hey, I'm telling you to divide by x minus 2 because I already know it's a factor. And then I would tell you later how I knew that. Well, the rational zeros theorem is how I knew that. So now that we know a factor, I can use long division to go get other factors. So back to the example at hand. This is a cubic polynomial. So if I go divide by this factor, the quotient will be a quadratic. And we know everything there is to know about quadratics. So that'll take us the rest of the way home. So next on the agenda would be to divide. So we'll do our long division here. So 2x squared would give me 2x cubed. Then we can subtract, get 13x squared. Then we'll get 13x squared minus 13x. And then, let's see, negative 7, that'd be 6, minus 6, and then we'll have plus 6. And then we subtract, we'll get 0, which is no surprise because we already knew that was a 0, and we already knew that it was going to be a factor. But what we didn't know was this quotient. So here's where we're at. We know that f of x, which was this cubic, we now know that it factors into x minus 1 times 2x squared plus 13x minus 16. Oh, wait, can't read my own handwriting. Let's try that again. Plus 6. And remember, I'm trying to find zeros. So plug 0 in for y. And we can use our zero product property. We get x equals 1, which we already knew. No surprise there. But we have this quadratic now. So all quadratics can be solved with quadratic formula. And I believe we get negative 6, negative 1/2. You can run that through a calculator. We don't take your calculator away from you. So now we know all the zeros. And it turns out they're all real. Those are 3 real numbers. So my zeros, my real zeros are 1, negative 6, and negative 1/2. And those are all multiplicity 1. And they're all real. So, which won't always happen. Sometimes we get non-real zeros. All right, let's go look at another one. So this time, it's presented in a slightly different way. We have a polynomial. It's right here. It's a 6th degree polynomial, but it's just already set equal to 0. So instead of this equaling y, so y equals that, it's already got a 0 plugged in for y. So it just becomes a polynomial equation that we want to solve and find its solutions. But it would be no different than what we just did in the previous example, where we just want to factor it if we can, and then plug 0 in for y and set the factors equal to 0. It'd be exactly the same thing. So the fact that they've changed the wording on us and said, hey, look, here's a polynomial equation, go find all its solutions, its real solutions, doesn't change our work at all. We still want to factor this thing. So let's go find my factors of p. Let's see. Let's see, so factors of 84. Well, we know 1 goes in there. We know 2 goes in there. 3. We know 3 goes in there. 4. 5's not going to go in. 6, no. Let's see, so 6. 7 does. Let's see. So I think 12. 14. So I think that's it. So let's see. We miss any here? And then our factors of q. Well, the leading coefficient is just 1. So that's handy. So my possible rational zeros, which we just take all the p values and divide by all the q values, but q is just 1. So when you divide all these by 1, you just get that exact same list. So it's just this again. So we end up with all these same ones. So that's a pretty lengthy list. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. It's a whole lot of numbers. So again, I'm not saying it can't be any of the larger ones, but that's not where I would start looking. So I'd kind of start on the low end and see which one. Some of them you can check pretty quickly without a calculator. Like if you plug a positive 1 in there, these numbers are so big at the end that plugging a 1 in is not going to get you there. Because your last two are going to give you a negative 168. So these first 4 terms aren't going to be positive 168. So some of them you can kind of ignore. Let's check, let's start with the 2's. So if I plug in a positive 2, I start to get some pretty big numbers. Let's check negative 2. So if I plug negative 2 in, Let's see, 64, 32, I think we get 0. So we just found one. So that means that x equals -2 is a 0. Therefore, x plus 2 is a factor. Well, if I go to divide right now, so if I was to divide this 6th-degree polynomial by this 1st-degree polynomial, I'd get a 5th-degree polynomial. Well, I don't know how to factor all 5th-degree polynomials, so I don't know that that's going to be all that helpful. It'd be nice if we could find some more zeros so that when I go to do my division, I end up with something I actually know how to factor. Well, that means I'd have to go plug in a whole bunch of other numbers. Remember, we got like 20 some numbers to plug in to see if we can find any other zeros. Well, I don't know about you, but I don't want to do that. It's a little daunting. So why don't we go ahead and use some of the knowledge from our previous section about the graph of this particular polynomial. So we can go graph this on Geogebra. So if we go graph this on Geogebra, here's the graph. And if you look at the graph right here, we see that it appears that the graph bounces off at -2. It touches the x-axis at -2 but doesn't cross it. So that's an indication that that's an even multiplicity. Well, the other thing we can see is that it has 2 more x-intercepts, so there must be 2 more real zeros, at least. But they're not integers, so it's not crossing at an integer value. They could be rational, except if you go look at our possible rational zeros, they're all integers. So what that tells me is this real zero and this real zero are irrational. So our only hope of getting another zero is the fact that this has an even multiplicity. So the graph bounces off, but it doesn't cross at -2, so we have an even multiplicity. So our only way forward is using the even multiplicity of -2. So from the graph, and yeah, we use GeoGebra for that, which is fine. We see that x equals -2 might have an even multiplicity. So that means it's a 0 twice. It could be a 0 more than that, maybe, but let's not worry about it. We're not sure, but we think based off the graph, it's at least a 0 twice. So now I think we can do some division and see if we can get somewhere. All right, so my zeros, well, I know -2 has an even multiplicity, so it would go backwards to x plus 2. This one would go backwards to x plus 2. And if I multiply those together, I get this quadratic. So since those are zeros of this polynomial, then this quadratic must be a factor of that polynomial. So let's divide and see what happens. All right, so we got to do this division here. So we get, oh, I skipped a term, didn't I? So we go from degree 5 to degree 3. So we got to put a degree 4 in there. All right, so we get x squared Then we subtract, let's see, negative 20. And then minus 20x. Then we're going to subtract those. Let's see. I totally forgot about my x to the 6th, didn't I? Forgot about my x to the 6th out here. Let's try that again. So let's see, x squared times x to the 4th. And then that would be 4x to the 5th. And that would be 4x to the 4th. There we go. Now I've got my x to the 6th accounted for. And then we'd get, let's see, negative 4x squared. Then when we subtract, that'd be 0, that'd be 0. So then we're going to do 37 minus 16. Oh, whoops. It's going to be negative 21. So minus 21. Then we get our remainder of 0. But again, that's not a surprise though. We already checked the negative 2 as a 0. And the graph told us that it was a 0 at least twice. So now, this polynomial we know it factors into this quadratic and this quartic. But this quartic is of quadratic form, so we can factor it. And now we're left with these two quadratics. So let's see, my zeros are going to be negative 2, which we already knew, negative 2 again. Then we're going to get, let's see, principal square root of 3i, although I should probably write that. Then negative I principal square root of 3, but those are non-real. And then we're going to get principal square root of 7 and the opposite of the principal square root of 7. So we end up getting 6 zeros, but 2 of them are non-real. So the directions were to only find the real solutions. So the real solutions are negative 2, multiplicity 2, and then principal square root of 7 and the negative principal square root of 7, the opposite of that. So those are my real solutions. There are 2 that are non-real though, so these, for now, we're ignoring. We weren't asked to find those, so we'll just kind of let them go. Okay. Last little thing here. So if only if only real numbers show up as the coefficients of our polynomial, which those are the only polynomials you guys have seen and are going to see this year. So as long as the coefficients of the polynomial are real, then there's two things that can help us out with this process. The first one is that any such polynomial can be factored into linear and or irreducible quadratic factors. These would be factors that can't be further factored using only real numbers. And then the other thing that's helpful is any odd degree polynomial has at least one real zero. That's because odd degree polynomials, they always point, the far left and far right side point away from each other. So if the far left points down and the far right points up, it has to cross the x-axis somewhere. And then if the far left pointed upward and the far right pointed downward, the only way that can happen is it has to cross the x-axis somewhere. Because remember, all polynomials are continuous functions.